Okay, so I'm going to go over this problem, and my suggestion was to try process of elimination. Okay, so we're going to eliminate the choices that we can say for sure are not necessarily true, and then I'll just show you why the one that is true is true. Okay, so if f is continuous on the closed interval AB, which of the following is necessarily true? So, first of all, guys, I just want to talk about a couple things. Okay, here is a graph that is continuous but not differentiable. Differentiable would mean that the derivative exists everywhere. And remember, at sharp corners, the derivative does not exist. Okay, the tangent line coming from the left does not ever start to match the tangent line coming from the right, so the derivative does not exist. So here's an example of continuous but not differentiable. Here's an example of continuous and differentiable. So the point is, guys, is that differentiable means two things, continuous and smooth. So differentiable means continuous and smooth. A continuous function does not need to be smooth, okay? Example right here. A continuous function does not need to be smooth, so a continuous function does not need to be differentiable. So here we have two implications. Just because a function is continuous does not necessarily mean it is differentiable, but since differentiable means continuous and smooth, if a function is differentiable, then for sure it has to be continuous. Okay, so there's just some preliminary information. Okay, now this first one, f prime exists on AB. Okay, f prime exists on AB means f is differentiable on AB. And guys, right here for A, I am showing a counterexample. Okay, so here's a situation where f prime does not exist everywhere on AB. Okay, so process of elimination. B, if f of x sub 0 is a maximum of f, then f prime of x sub 0 equals 0. So guys, right here, they're assuming smoothness, okay? So for part B, they're assuming like a situation like this, you know, where you would have f prime equal to 0 if, you know, if we've got a max there. But here I am showing you a counterexample. All they told us was that f was continuous. So here's a situation where f is continuous, but at this max, f prime is undefined. Okay, so since it's not smooth, we don't have a horizontal tangent. So B. C. The limit as x approaches x sub 0 of f of x is equal to f of the limit as x approaches x sub 0 of x for, what this means here, guys, is that x sub 0 is an element of this set. Okay, this means element of. Okay, now we have never really seen anything like this, so let's just skip over it and move to the next thing. F prime of x equals 0 for some x in AB. Well, guys, a continuous, all we know is that f is continuous. It could be a line, all right? It could be a line, and nowhere here does f prime equal 0. That would mean we have a horizontal tangent. So we don't need to have a horizontal tangent just because a function's continuous. And then E, the graph of f prime is a straight line, not necessarily, okay? If f is continuous, it can do a lot of things. So here we see that the answer is C. All right, now let me show you an example of that. And this is actually a true thing. If you're taking the limit of a continuous function, you could put the limit like inside of the function. We don't normally do this, but let me just show you an example. So radical x, that's a continuous function. This is the graph of it. Now, let me show you two things. If we do the limit as x approaches 4 of radical x, we get 2, okay? You could do direct substitution, radical 4 is 2. But, guys, we get the same answer if we put the limit inside. All right, if we take this radical and we put it like outside of the limit, we get the same thing. So radical limit as x approaches 4 of x, 4 just goes in for the x, and we get 2. All right, so there's that.